Hey guys, I hope that you enjoyed the previous section lecture. I just wanted to ask you to please email me if you cannot follow the lectures or if you do not know what to do. Now, I created an online quiz for you. I think it was yesterday or the day before yesterday. So it's just like a very general question about the class. The purpose was just to understand if the online quiz and online testing is working correctly or not, because I have not used Blackboard before this class. Okay, so today we're going to talk about Chapter 24, Section 2, and hopefully Section 3. So let's talk about capacitors in AC circuits. In the previous section, we learned about resistance in AC circuit. When I have a capacitor in the circuit, so again I have an AC generator that produces the voltage RMS with the angular frequency of omega, and then I have this symbol that stands for C, as you all know. Now, in the AC circuit that contains only a generator and a capacitor, the relationship between the current and voltage is different in many important respects from the behavior that we previously saw with the resistor. So what we are going to study in this section is that in such a circuit, what is the RMS current relationship with the capacitance of the capacitor. So there are several methods to just write down the equation for the current and solve it, but in general, I'm just going to give you the solution to such an equation. So we know that according to Ohm's law, V equals to Ri, and then from here, I can write that I equals to V divided by R. So this is very common. Now, if I want to define the RMS current for the circuit that only has capacitor in it, then IRMS equals to VRMS divided by XC. In this expression, XC is the capacitive reactance. So XC is capacitive reactance. So you see the similarities between R and XC. So basically they are both types of resistance in the circuit. While R shows the resistance in the circuit because of the resistor, XC shows kind of resistance because of the existence of the capacitor in the circuit. Okay, now it is important to define XC in terms of the quantities that we know. So I can define XC to be 1 over omega C. Omega is the angular frequency, like we had before. And that omega was 2 pi F. And then C is the capacitance of the capacitor. Because XC is a kind of resistance, the resistance that a capacitor has, so it has the same unit as a resistor. So X sub C has the unit of ohm. Okay, let's take a look at exercise 24.4. Find the capacitive reactance of a 45.8 microfarad capacitor in a 60 Hz circuit. So in this equation, in this exercise, I know that the capacitance is 45.8 microfarad and that the frequency is 60 Hz. And I know that X sub C equals to 1 over omega C. So what I need to do here is that I just need to replace the numbers here. So omega, we knew that it is 2 pi F, and then C is C. So I just plug in the numbers, 2 pi times 60 hertz times 45.8, and then times 10 to the power of negative 6 to convert the microfarad to farad. So if you calculate this, you get XC to be 57.9 ohm. So again, the unit for the capacitive reactance is ohm. So once you know this X sub C, then you can find the current if you know the voltage. Now let's take a look at exercise 24.5. It says suppose the capacitance in figure 24.7 is 6.25 microfarad and the RMS voltage of the generator is 120 volts. Find the RMS current in the circuit when the frequency of the generator is 60 hertz. So I can write that omega is 2 pi f, and I know that f is 60 hertz, and then I can find x sub c to be 1 over omega c. So this is the calculation, very similar to the previous exercise. So before I plug in the numbers, I just find the equation for IRMS. So the current RMS equals to VRMS divided by XC. Now, if you replace XC by 1 over omega C, then you can find IRMS to be omega C VRMS. Now it's just a matter of plugging the numbers. Okay, so instead of omega, I put 2 pi f. Now I'm plugging the numbers. And then, after calculating this, I can find IRMS to be 0.20 amps. Alright, for part B, it is exactly the same thing, except from that the frequency is reduced. So if you compare the numbers for the IRMS together, you can see that when the frequency is reduced, then the capacitive reactance becomes larger. As a result, the RMS current decreases. So this is an important conclusion to notice. Okay, now let's take a look at how the phasor diagram looks in the capacitor circuits, or basically how current and voltage react to each other. What you can see in this figure here is the voltage as a related to time, or better to say versus omega t. So if I plot the diagram for voltage versus omega t, I should get a diagram that looks like this. Okay, now if I plot current versus omega t, it should look something like this. So you can see that current and voltage, they have a phase difference, that they're unlike the previous case, which we only have resistors in the circuit. When you have the capacitor, then the voltage and current are not in phase. There is a half a pi phase difference here. So this 90-degree difference between current and voltage can be seen in a phasor diagram if I plot the phasor diagram for this. The phasor diagram should look something like this. So here again I have the Vmax, which equals to Imax x sub c, but then the Imax is at 90-degree difference with the Vmax. So we can say that the voltage phasor lags current phasor by 90 degree in the circuit that only has capacitor in it. Now, this theta here, like the previous case, is the omega t, and then if I project the I maximum on the y axis, it should give me I max sine theta. Now, if I project the Vmax though on the y axis, so if I project the Vmax in the y direction, then the component y of the Vmax is going to be Vmax sine theta minus 90, which is the sine of this angle here. Now let's take a look at the example 24.6 in your book. It says consider a capacitor circuit as in figure 24.7, where the capacitance is 34 microfarad, the maximum current is 1.45 amps, and the frequency of the generator is 60 Hertz. At a given time, the current flowing through the capacitor is 0.95 amps, and it is increasing. What is the voltage across the capacitor at this time? So what I'm going to do here is to draw the phasor diagram for this so that we understand what's going on. So we first recall that the current has a positive value and it is increasing. So I'm going to draw I max in the positive quarter, and then because it is increasing, this is going to be the omega. So the fact that current is positive means that it must point in a direction theta between 0 and 180 degrees. The additional fact that it is increasing means that theta must be between 0 and 90 degrees. Now if I drew I max somewhere here, so which now I know that it is wrong, this would mean that the current is decreasing with time. So it would be the positive current but decreasing one. So this is not the case. I'm gonna erase this one here. So that is I max that you can see. Now let's just draw the voltage. We know that voltage phasor lags behind the current phasor by 90 degrees in a capacitor. So this is my voltage phasor here. Okay, so we need a scenario for this problem. First of all, we know that the maximum current I max and the instantaneous current has this relationship with each other, that I max sine omega t. So this is what we know from equation 24.2. Okay, now if I know theta, which means if I know the omega t, then I have the I max, I can find I, and when I find I, then I can find V. Next, I know that V max equals to I max times x sub c, which is indeed equal to I max divided by omega c. The third fact that I know here is that V max, and excuse me for this, V equals to V max sine theta minus 90 degrees. And this is something that you can see from the phasor diagram. So this is V equals to V max sine theta minus 90. So this is the y component of V max. Okay, now that I know which equations I need to use, I'm gonna write down the known of the problem. So I know the capacitance, I know I max, I know the value for I, and then I know the frequency. And what I need to find is a V, not V max, but just V. What I don't know in order to find V is the theta, but I know I and I know I max, so I can find theta to be sine inverse of I divided by I max. So in order to find theta, I just plug in the numbers for I and I max. It's going to be sine inverse of I divided by I max, and it will be 40.9 degrees. Now that I have theta, I can go ahead and find V. from the equation V equals to Vmax sine theta minus 90 degree. Alright, so let's find Vmax first. Vmax, as usual, is going to be Imax divided by 2 pi Fc. Let's plug in the numbers and do not forget to convert the microfarad to farad, and then our maximum of voltage equals to 113 volts. Alright, so now I have Vmax and then I have theta. I can just plug in the numbers and find V to be 113 volts times sine 40.9 degree minus 90 degree. So if you calculate this, the voltage at that time that I is 0.95 amps is negative 85.4 volts, and that's your final answer. Okay, so this fact that voltage becomes negative could even be seen from the phasor diagram. If you see this diagram again, you see that the y component of V is pointing downward. So we expected to have the negative number for the voltage, and that is totally fine, because remember that this is the AC current, so that the direction of the voltage is always the direction of the current is always changing, which yields to negative values for the voltage. Okay, this example brings us to the end of section 2. So we'll continue with section 23, and that is the case when we have both resistor and the capacitor in the circuits. Please let me know if you have any question. Again, if the lecture is not clear enough, we have a discussion board for this week. Feel free to post anything, absolutely any question that you have, or email me separately, and I will get back to you soon.